right. Good afternoon, everyone. Here we are for the 2 days online workshop on FEA modeling. Day one, it will be about FEA modeling on wind turbine nacelle covers. It's going to be presented by Mr. Parthasarathy Ravi. Let me introduce the guest for everyone. Mr. Parthasarathy Ravi, he graduated in SRM University in 2008. And then in 2009 to 10, he worked as a design development engineer in composite glass fiber products. In 2011 to 15, he worked as a senior mechanical design and stress analysis for wind turbines. And in 2015 to 17, he worked as a senior mechanical vibration engineer in wind gearbox. In 2017 to 2020, until date, he's working as a supply chain officer, cost analysis in wind turbine, and currently he's working in the vibration analyst as a vibration analyst in CAT 2. Mr. Parthasarathy Ravi is a mechanical design engineer professional with variety of expertise in new product development, specialized in wind turbine technology and gearbox design. He has varied level of expertise in design development of large structural components and vibration analysis simulations. He has hands-on experience in structural analysis of heavy engineering components using FEA and carry out what-if case analysis. Present reports to certification body for prototyping. He has rich experience in pre-processing of wind turbine loads using GH bladed simulation, carry out wind turbine drivetrain simulation using SIMPAC and DRESP for modeling and design vibration. And I'm very glad to announce that he is my undergraduate classmate and college mate in SRM University. Now I welcome Mr. Parthasarathy Ravi. Over to you.
Thanks, Amos. To give a short introduction about myself, is my voice clear to everyone? Thank you. Okay. Sometimes I may have to speak in Tamil as well. Please forgive my language. But then, being away from India, still I would definitely would try to put in different ideas using languages because I'm a multifaceted language person. Although I've been born in Tamil Nadu, but then I've brought up in other parts of India like Rajasthan and Andhra Pradesh. Like to share my experience, how I started my career. As Amos said that I finished my master's in aerospace and then didn't know where to start. For 1 year, it was completely vague, where just like you, any graduate engineer trying to know where to pitch in into the industry. But then always there was a desire and passion about wind turbines, and I fortunately had a breakthrough in one of this. The most smallest component is the nacelle cover, and nacelle cover forms the major part of the wind turbine designs. Fortunately, I started with a very small company which does supply to major MNC companies like Siemens, Vestas, or you need. Yeah. Right. Okay. So that. Yeah. I'm not sure whether the lighting is sufficient. Anyway, I'll also start presenting from the. Is the video in full mode or how is that? Okay. Let me. Yeah. So I was fortunate that I started my career in glass fiber industry and started designing, or not even straight away designing, but then as a production engineer working in a small company called Suvarna, which is still there working in Vellore, which is not pretty far away from your university. And then I had a chance to interact with most of the customers who are in the wind farm field, and they were a bit surprised, like being an aerospace engineer, why did you start a career in nacelle cover design and all those things? But then my future was well written. I did get selected with a customer company itself, like who for whom I had developed a nacelle cover, where they didn't have any idea about the problems on the nacelle cover. So these were all my first year of engineering experience. How a customer without any knowledge, still they were able to develop the design, but then still they failed at the site, and just before it was getting into the assembly stage. So these were all the experience, like raw hand experience, without having any answers. These were all, as far as answers is concerned, it took me almost like 3 to 4 years. First, when I joined the company called as Garuda Vayu Shakti. That's where in the second year, I started my career in FEA. Till that time, when I joined, I didn't know what I was going to do. But then it was written that, okay, I would be a load engineer and also doing the complete wind turbine design. So I was part of the three-member team. So we were lucky, like when we started, the team was only 8 members. With 8 members, we still have put up a wind turbine, two of them, which is still running in Tirunelveli. Unfortunately, the startup company was able to only survive 7 to 10 years, and had to liquidate because of financial issues. Back then, was in 2012 and 2016. So not going too much into deep, I would like to start with the present company, which is ACOEM. We are into the wireless era of sensors, where we monitor vibrations of equipments which is rotating or non-rotating, try to find out the natural frequencies and do a modal analysis, do a correlation if it is a structure vibration or any kind of rotational vibration, be it any practical motor which is having vibration issues, like any shaft you take, it would have a bearing on either sides. We can detect the defects in the bearing much even before its failure, like 3 to 6 months, or like even 1 year before its failure. So that's the wireless sensor technology developed with ACOEM. The presentation part, where I'm going to speak about the nacelle cover and composites, has nothing to do with this company, but then we still support the wind division, where we monitor wind farms online in terms of its failures or failure prediction. So ACOEM is itself, the name or abbreviation is ACOEM, but then how it is a derived name from based on rotating equipment and environmental division. A combination of that is an acronym. We specialize into noise monitoring as well, for example, and as well as the environmental pollution. If you had ever come to know the PMI index, which most of the Bureau Meteorology people publish, PMI index, or your health index, those devices are all procured from us for all the government agencies, and they publish in the live stream data how good it is. Like for example, in Delhi, when the PMI index was pretty high, like 225, 250, or 400. So where are these numbers coming from? So those instruments are all produced from us. We have 700 plus employees, and we are based in the headquarters is in France. That's where the technology was born, and still they are patenting in across various acoustics as well as vibration technology. We are also based in US, and as well as in India. We have an R&D center. We have probably 15 plus team members there working out, as well as in Australia and in Southeast Asia. Probably I can play directly a short monitoring video. That would be much better. Probably you can have a look what exactly these products, what I'm talking about. Are you able to see the screen? Yeah, thank you. Time to time I have to ask for a feedback. It would be appreciated. Right. Um, Not sure what has happened. You are not able to get the audio of this. Okay. The only option at the moment, I can only play the video, and still the slides are still there for you guys. You can look at any time. Probably I can directly jump onto the slides instead of too much wasting on the product what we have. Definitely, there will be another time where I can explain what we do. Right. So going on, apart from the vibration monitoring, what we support for various industries, be it processing or wind farm or mining industry, you name any industry, our products plays a vital role in getting the data collection, trending the data analysis, and gives the end user what results are they want to achieve. That's what where we support from, right from implementing and executing the solution. Now moving on to the design of nacelle cover. So the topics or the contents, what I would like to show you through is walk you across is an introduction how the nacelle cover designs were done right from history, how in probably 20 years ago what you see the composite glass fiber was not actually composite glass fiber, it was only the steel. All the parts what you see here outside is a nacelle cover, and basically this part before the invention or the transition to composite glass fiber was completely steel and it was pretty heavy. This particular turbine is a turbine from Garuda Vaishakti. That's the first design which we did. The design is the complete drivetrain design. When I say drivetrain, means this is the rotor, the gearbox, and the generator. This is called a complete drivetrain system for a wind turbine. Now, how crucial is nacelle cover? If you see um, nacelle cover, it plays a major role in onshore as well as offshore turbines. If you see the advancement in offshore turbines, some of the turbines do have an helipad system for a person to be dropped on the top. To that extent, the loads gets onto the nacelle cover. Some of the advanced onshore system wind turbines have gotten built-in AC systems as well, having many more options that the nacelle cover can handle. So during my start of the career, I had literally no idea what the nacelle cover's impacts were, how it was crucial. It is like also like a person can be standing somewhere on the top of this for service point of view or even for maintenance point of view if a crane has to come in and drop in to remove some components. So yeah, he would only depend to stand on this cover, believing that okay, the cover is structurally safe, no problem if he's trying to anchor his I would say a seat belt, but then it is called the harness. The harness would they would try to buckle up on the top of the turbine. There will be sometimes wind will be as fast as like 60 kilometers per hour, but then they know that conditions when the wind is very high, they won't go outside on top of that. So looking at the design process of the whole turbine, the turbine modeling, definitely it starts with the modeling. You need to make an estimate what is this length, width, and height of the whole nacelle cover is. There are various designs. Some of the designs, for example, like if you take Vestas or if you take Wind, every company has got a different approach. How many parts of the nacelle cover it should be? Like for example, generally, in the sense it comes in a three cover part, that is nacelle top cover, bottom LH, and bottom RH, and then they are assembled in the factory before it gets out. This is one approach. The other approach is putting up a cover from the bottom. When I say cover, it's not normal plastic cover. It's the wind turbine nacelle cover. We say top is nacelle top cover is this, bottom LH is this, and the other side is bottom RH. In the upcoming slides, you will definitely know what I'm trying to. Some of the terminologies may be new. But if you are having a background with wind industry, then you will be able to easily pick up. So that's what the design stage, where it is completely made sure, okay, the whole length and every part inside as well is also be able to speak with the nacelle cover. For example, when I say every part, in the sense, if you see this components inside here, you would see that this is the generator. It has got an exhaust, and it has to also interact with the nacelle cover from the outside, in the sense that trying to blow up the hot wind. So it needs to have an exhaust system at the back, so that there's a window, and that window is exactly aligning with this generator. Second thing is that, for example, now here you see this bottom part is the tower. So you will need to have a circular cutout in both sides of the nacelle cover. So, and exactly matches when it has been assembled. So tower usually is not assembled on factory. It comes straight to the site, and anything goes wrong, we have to cut out with the nacelle cover. There have been so many problems. Even you see here, there are internal cranes which has been there. The purpose of this crane is to make sure that, okay, if there is a motor which could be weighing about 50 to 100 kgs, it is not easy for an technician to lift it up on his own. There would be one more person, the lift inside will be able to help him out. But then some of the designs have incorporated the lift or these cranes beams holding up with this nacelle cover. They are sandwiched with the nacelle cover so that the nacelle cover can hold that weight as well. So the complexity keeps increasing. Some of the nacelle cover has got a built-in air conditioning system where to keep the complete temperature around 25 to 30 degrees Celsius. So they have built-in thermal AC system. So we need to see that, okay, are we incorporating those kind of system? It doesn't fire up. Yes, on the fire, there are some, most of the offshore systems are built in such a way that they are fireproof, but then it cannot be still guaranteed that if the flame is beyond certain limit, definitely the whole nacelle on the top can burn still. So going on the design modeling, that's all. These are all the aspects that are looked in the design stage when it is built up in using any of the CAD model, like you can say SolidWorks or AutoCAD or ProE. You can use any of the tools. There's no limitation for that. On the stage 2 is the strength assessment. This is where we would be mostly dealing how the strength analysis point of view is taken care. A person standing on the top of it to holding on the rail on that, to having a thickness built up and seeing its strength and structural rigidity. Then also to verify different aspects of loads. Followed by that is the actual, this is all done into a desktop simulation, not in actual practice as well. When we say that everything is good to go in terms of manufacturing, in terms of its strength and all, yes, then it goes to have the first prototype model ready in actual full scale. This stage 3 itself was my first 1.5 years of experience building up the 3D model to an actual real scale model. So this itself, it could be again 1 hour lecture because that itself details about how the pattern and mold of the nacelle cover is formed, and then the serial production is commenced after that. Please feel free to stop me anytime, ask a question or any clarification. What does this terminology mean here? Or you have any doubt? Don't anytime you can ping in. If you are, my accent is little bit got a little bit Australian accent because day in day out we are forced to speak only in English here when you are in public or on outside anywhere you go. If you are unable to understand, please stop me. Or you say you are not able to understand, I can still change my language so that you are all happy, and whatever you try to learn today, you take it with you. So as I said that what is the purpose of a nacelle cover? it would house all the critical components, gearbox, generator, control systems. That's part of this. Whereas the spinner cover or the hub cover would cover the rotor side, which is also just the initial stage where you see these openings. That's where the blades comes in and joins onto the hub cast, which is also a metal part sitting inside and trying to drive the drive shaft. If you could see here, this is a proper cut section, how it looks like, and it has also got uh, communication control systems built in so that it would try to drive the blades and then get the torque transferred to the main shaft. So the spinner cover is also a pretty very much essential part of the strength analysis. So this also comes sometimes in three, most of the time it comes in three parts. Like at this stage, this is assembled. Like you can see part one here, part two here, then there were two more parts on that side, and there's a cover on the top. Some of the entry, we were fortunate that if you have to access the rotor hub inside for some kind of problem for a technician or for any kind of maintenance, we can get through this manhole straight from the this. If you are standing here, you can get inside straight like this. But then there are some nacelle covers that were not properly designed, looking into safety of the technician. It is like coming outside on top of this, standing on top of this, and getting it from here outside. You will be almost like there will be a rope which will be holding you, and you will be getting inside from the front. There is a definite risk. So there is a key importance how spinner covers are designed in today's probably in the last 10 years, the design has mostly changed to make sure that the technician doesn't enter from the top, from outside, rather than he can straight away walk in from inside. So as I said, the nacelle cover parts, so they have more functions of like in terms of its stiffness. When I mean stiffness, they have to also hold their self weight, and also they have to have the ability to not to buckle in. There is also, like you could see here in this picture, that there are some gussets which look like this, and they hold up to the cover on this LH cover, which is a left side cover, and then they would attach to the assembly to the main frame. So that's how this cover both comes on either side, and this comes from the top side. So this was my first project where I was assembling these three covers, which is bottom left, bottom right, and top. This was in a small workshop very close to Sriperumbudur. That's the first place where we assembled this prototype nacelle cover. And in the initial stage, the cover was designed without the designer properly not knowing what was the material property, and they didn't properly look at uh, the deformation issues with the cover. So there was a structural defect with the cover. As a supplier, we didn't know. We all believed only what 3D model was given and what drawings were given and how to build it. This is what our scope is about as far as a supplier is concerned. We were not sure that this cover had a structural defect. But then as a supplier and as an ongoing contract with them, we provided an on-spot solution how to remove the defect. But then that had to be still validated and then given for better engineering design. So this is where you will learn how to eliminate structural defect when you find one. So in this case, this was my first engineering experience. So this cover is one points on megawatt cover. So in wind farms, we say always 1.7 or 1,700. So this 0.84 stands here for the rotor diameter, and it is able to drive 1,700 kilowatt of generator power coming out of this. So as you see here, the length of this cover was about 6 meters, and it's about 3 meters just with the bottom cover. Whereas the top cover itself has got an again probably 500 mm to 600 mm, and still the same length. We have to also make sure that this gap which is there is also, like, before it gets out of the factory, has got enough silica gel. It's like a silica paste to make sure that the rainwater doesn't creep in. So this is the factory where I worked first. It's called Suvarna Fibrotech. It's still operating out there, and we were making this cover for a company called Win-Win, which was the first 1 megawatt turbine. For them, it was pretty much aerodynamic cover. As you can see here, it looks like a two-part, but then it's not a two-part. Like the part from here, and the top one single segment is combined. That's how it is, like, bolted all through its length. This was standing about 9 meter in length and 4.5 meter diameter in complete dia when it is assembled. So what we had to show was that to customer, that every time before we send out this product, we have to assemble it, take a picture, show them that when you put up the bolts, it will properly align. There is no problem when it goes into their factory with all the internal components fitting in. So this was my function, part of the job when I started as a design development engineer. The picture at the back, what you see here is the mold which has been developed for this, and that's where my first project was also, like, developing the mold for this particular cover. This is the hub cover for 1.7 megawatt turbine, again Garuda. Here you can see this is sitting inside the nacelle assembly floor plant, and we had to make sure that before the whole turbine is dispatched, we have to make sure that this cover is on and it is being properly covered without any scratches, and then make sure that we have done all the due diligence for quality point of view. So as I said earlier, that nacelle and as well as the blades were actually made from steel. Going back in 1990s, blades were made, even 1980s blades were made in steel. The material which for nacelle cover or hub cover, what you see here is isophthalic and the glass fiber material. Isophthalic is the resin, glass fiber is the layer which binds this with the resin to form the final component. I would be speaking about the combination, how it forms. So the material was definitely borrowed from the aerospace engineering domain. It has been predominantly used in aircraft structures. So nacelle and blades, blade is especially made the 1990s to 2010, who are made by epoxy glass fibers. The epoxy is the resin and the glass fiber is the same fiber content. And now it is going to some stage where the blade root is made by carbon composites and also a mix of epoxy. So the root is made by epoxy and the rest of the blade length is made by epoxy. Sorry, root is made by carbon composites and the rest of the blade is made by epoxy one. The main advantage was that they were able to design the shape using these materials, and it was easy to refit. If there is a problem, let's say there is a damage when it has been lifted up, you can still easily patch up. Like, you can, if it is on the ground, it is easy for a technician, fiberglass technician, to come, and it's like a fracture repair. There is no structural point of view. If there is a fracture or there's a blow, there's a hole that has gone through this, there's nothing to worry that it will, the crack will not still penetrate through the rest, except if there is a delamination or a air gap within this material. So it was pretty easy to fix this if there's a damage. So as I said that about the material, what it is called an anisotropic material. Why anisotropic? Because it is very much direction dependent. Unlike steel, if you take even the smallest square plate of steel, it is isotropic in material. That means isotropic here means if you give force on that material, the directions will be in all the sides. but the force propagation or penetration or through the passing of the force will be in all the directions. But whereas in ionoset composite material, that's not the case. The fiber orientation plays the major role. If you hit, um, for example, if you take the blades, the whole length of the blade is where the fiber orientation is mainly concentrated, and then they would have a warp and weft across the other directions as well. But then the majority is in the length of the direction. They also know that since the blade is cutting through the air, they will have 0, 45, 90-degree orientations of the fiber. Uh, this is how it plays. As far as nacelle cover is concerned, there is no hard and fast rule as like to put it in 45-degree or any other degree, but then usually they would go with a 0 and 90-degree bidirectional mats, which is like you can find it readily available with most of the suppliers, and that's what it is preferred. There is no, as such, I've not found any papers which says that you have to use in a specific direction unless the load keeps changing. So in the bottom side, as you said, as I was speaking about fiber and the resin. So in usually if people are not aware, the first time whenever you are a graduate or just an engineering student coming out, it is always termed in terms of matrix and reinforcement. This is how the matrix and reinforcement would stand like. Like the matrix is the resin, which is the liquid part of it, which what happens to the liquid is, like I can show you in the next couple of slides. The resin is a very viscous, I say not very highly viscous, but then it's like a gum kind of a material. And it comes in three formats. One is isophthalic resin, vinyl ester resin, and epoxy. So usually in terms of cost, isophthalic is much preferred. This material is not used predominantly in any blades, but then this is only for nacelle cover and hub cover. Some of them covers they use vinyl ester. If you see the boat fabrication, like any speed jet boats, they will have vinyl ester as well as epoxy combination. Whereas blade is concerned, that has been transformed from steel to epoxy. Even the nacelle cover, that's the same. So epoxy is the resin, fiber is the different kinds of fiber that's there. For example, if you see EC, E means in E glass fiber, that is a little bit of electrically insulated glass fiber. C is chemically resistant, that's a different kind of a fiber mat. And then we have across different countries what designations of different fiber mats they can produce. So as I was speaking about bidirectional mat, a bidirectional mat is simple 0 and 90 orientation of mat that comes only like that. As you can see here, it is 0 in this direction, 90 in this direction, and that's how they are designated. So the combination, the fiber also comes in the form of a chop strand mat like CSM 300, 450, 600. What does this mean is like the grams per square meter, like 300 grams per square meter is what that designation stands for. Probably when you want to look at an actual how a chopped strand mat looks like, this was taken from my supplier's workshop place on my phone. So this is how closely a chop strand mat would look like. Here on the right hand side is an hand layup being done for a different component. Normal roll from any industry, a glass fiber industry, they would be giving the raw material in this format. So as I was jumping between the chop strand mat and bidirectional, now I would also try to tell you that, okay, on the right hand side, this is like the cover which had shown you in the previous slides, the wind nacelle cover. Here you can see that the base, the wind nacelle cover was at 10 mm thickness. So what they would do is like you have a mold, and on that mold you put first a couple of layers, probably building about 4 millimeter thickness along with the resin, then make it to harden, which will take about a day or two. because it would, once it starts hardening at the time, this is like an exothermic reaction. When you can't stand on this, it will be almost like 90 degrees Celsius. And then they also put a foam. This is to improve its structural stiffness of the nacelle cover, as well as to build up the thickness. So foam is a different kind of an property itself. That is like the density is very low, like 2 gram per kg per meter cube. That's how they are, and it is very much flexible. It orients to the different shape. The only problem with this is like when you are trying to uh, assemble with this layer, this will be very much solid and it would be very rough. Whereas if you have to stick with this, the bottom side of this has to be resin impregnated, and we have to make sure that there is no air gap. What here air gap means is like if there is an air gap, then if it is has bursted, then there could be a layer cracking along the length, or depends on where the air gap has started to propagate. So this is a very much delicate operation. So we have to be very what we have learned is very careful to when we use the foam in an nacelle or a blade material. Similar would be also a blade. Blade does also have foams incorporated in their material. The thickness will be very much varying from the root to the tip. As far as the nacelle is concerned, the most of the time the thickness is a uniform thickness. There is no tapered in thickness for nacelle covers or hub covers.
Can I ask one question?
Yes.
What is the purpose of the fiber?
So the fiber is like if you had taken a steel plate, let's say a 10 mm solid steel, and you try to hammer it from the top surface. Let's say take this cube, okay, and you try to hammer it from the top. If you take it the steel, the force dissipation from the point of hitting and where you see, and you can try to measure from all the sides, the force will be equal in all the directions, in the sense that the force transfer will be going in all the directions. The stress will be different in different places, but then the force transmission will be in all the sides. But then if you take, as far as the fiber is concerned, the fiber as it is made up of glass strands. So let's say in this case, the blade is in the length of the blade. If the major orientation of this fiber is along the length of the blade, so that's where the force will also be mostly going. It's much like an electric current being passed on a wire. So if you have 10 wires, the direction of the wire where it is going from one side to other side, that's how the fiber would behave. Like, so it is a very much friendly to carbon composite designers or glass fiber designers or composite designers, using how to transform your forces in from one direction to other direction. So that's how fiber definition is. Is that clear?
Yes, clear, thank you.
Yeah. So the best idea is like if you go and see a manufacturing plant where a blade is being manufactured, that would be the best place. It would be like in this case, what you see on the right hand side, there is no absolute safety as far as the nacelle cover is concerned when they are trying to manufacture it. But then if you see the blade manufacturing, it is very much in a very neat fashion. There is vacuum infusion method that is done. It's not done using a hand layup, but then the initial stage is hand layup only. Like the first couple of layers in the blade is hand layup. So you could see there, the only problem is that you may get offended with the smell of epoxy resin. Sometimes it is very not easy for all people to accustom with the smell and the environment where you stand inside, that you may get itching surfaces on your skin. So I would definitely recommend. There are plenty of couple of blade manufacturing units in and around Chennai. So you can have a probably try to have an industrial visit for a day, and you will come to know how exactly the process is done. So as I was telling about my first engineering problem all through the initial slides, so what you see here, this nacelle cover, when as me from a supplier point of view or a design developer point of view, I had no idea whether this nacelle cover was having a structural defect. In the sense that when this cover was produced and was kept just before for dispatch, I just by for the sake of taking a picture or a selfie, I was standing right in the center on the top. It was just the height was not very much from the ground. It was less 2 meters above the ground, placed on a stand. But then, as soon as I stood up on this, the whole glass fiber on the top caved in. The sense it deformed in the center. So that was not a good sign. A nacelle cover shouldn't be doing that kind of defect. The second problem, what we found was that when this nacelle cover had gone to the site, there was a problem with this window not at its correct position. Or you may be wondering, why is this window? What is the function of this window? So in my different slide, there will be a reason for this. Why this window is placed in this location or this location? It's not for design or aesthetic point of view or looking good point of view. The purpose is that when the crane has its chains coming in to lift the whole nacelle, the chain has to pass through this and lift up the center of gravity location of the whole nacelle, and then it goes up along with the nacelle cover. This is how it is done. But then what we found in the site was that the chain was not going in its intended place, and it was away too far away from the center of gravity of the whole nacelle, and we are not able to hook up properly. So we had to remove this cover, and we have to do 2 times the lift. Probably will be too vague for you when I try to explain. Probably when you see another picture of that, you will be able to come to know how we had to overcome this problem of this window positioning. So this is the actual picture. This is just before the dispatch. We have to see that it is all properly aligned, bolted up, and then this is how it is sent. This was pretty easy looking before the sticker is on. On the right hand side, this is the sticker, how it looks like. This was on an actual site, the same nacelle cover, with 3 technicians also standing on the top, and still safe. There was no problem, where we were able to recover, improve the design defect, and made them an assurity that this cover, when you're on the top, it will not give away. So as I was speaking about the nacelle cover dimensions, so it was about these are the exact dimensions of the nacelle cover, and it had, the weight was, only the top part was 524 kgs with no foam. So it was all 10 mm thickness throughout, and it had a requirement as per the certification is that 4 people standing at on top of this in a 1 square meter, they should be able to have about 80 kg of load on top of it. Different companies come up with different methods to assess this. For example, when we were designing for Vestas, they asked us to hang a dead weight, like a dead concrete weight, which is about 450 kgs, right from the center, and hook it up and make sure that we make a video recording, show that there is no deformation on the top, and also make sure there is no leakages of water coming in. That's how we have to prove and dispatch in terms of quality and production. That's how is the way in which Vestas was asking their nacelle cover to be tested, because their cover had a reinforcement. The reinforcement is also called stiffener, in the sense that they sandwiched iron tubes or square hollow tubes along with the layers, so that it had a better rigidity and it didn't deform. So that was a problem with this nacelle cover. So going on to this is the actual predefined without the stiffener. And what would happen, this is the state I was feeling when the nacelle cover gave in. It was like, if you try to measure the deformation, probably it was about 100 mm down from its center point. So if you draw an axis line, I was down there. This was the defect that was able to get through. So there is also different ways of assessing it, like an average Indian person's weight. I had to specifically say male that because it was more male-dominated industry where you could hardly see any woman on top of the nacelle covers. So the weight would be 70, 75 kgs. But then if you take someone from Germany or in any part of other Europe, the weight would be 85 to 90 or 100 even kgs average weight. Had to specify specifically German because it was a German design. You would be a bit surprised why a German design engineering company was at fault. Unfortunately, they were not very much specialized with the glass fiber or the design of this, and it was a very different situation for us. But then as a supplier, we had to support no matter the company. We had to make sure the safety is the first priority. So how did I start? When I joined the company Garuda, this was my first project or to derive theoretically and prove that on a simulation basis using a finite element technique so that okay, we can solve this. So usually Euler beam theory is generally used for steel or which is in elasticity, which has like an elastic mode, but then Halfenside theory is specifically used in the blade industry or wherever the composites are. So the reason is that like Euler beam theory assumes that if you the elasticity of the material is like stress versus strain, or it follows the Hooke's law, like it would come back to its original shape and to the same state. Whereas that's not the same case with composite materials. There, since it's a thermosetting plastic, it would deform permanently in that shape. It would not come back to its same state. So the rule had to be changed, and accordingly, we need to calculate specifically what its Young's modulus would be. So you cannot just like use the Young's modulus of steel straight away. In the demo class, you will come to know what would be the difference. So in this slide, you can see on the left-hand side the actual calculation just based on a spreadsheet, how it would look like and how it can be, you can put those parameters in your ANSYS or any finite element analysis techniques. In this case, you can see that the engineering material for elasticity is striked off because it has taken in the orthotropic elasticity material where we were able to transform all these properties there, and we have to make sure that the density of the material is for the glass fiber, not for the steel. Any questions or anyone? Because it's a like 1.5 hours. At the time, I think now we are still a long way to go. Probably I'll try and finish this soon and jump into the demo as well in probably another 20 minutes time. Please feel free to ask questions at any time. So, okay, this particular slide is to test you all. Is this correct? If the what this I can define you the problem. This is a near look-like model of the nacelle cover. Probably it's like a mid-surface extracted material, and then this is the block of channel or steel or any kind of material. Is this orientation correct? Do you believe that in this orientation, if I keep and load on top, will this hold on? Anyone can answer from the audience. Do you believe this orientation of these blue parts will hold the weight in a better fashion, or is there any other orientation do you suggest? That's what my question is. What do you believe so? Okay, that's pretty good. Close answer. Any reason why is that? Right. Yes, this is right. Agreed. But then I had intentionally placed it in the wrong fashion. So you said 90 degrees. That's correct. Okay, I just wanted to listen exactly who else is telling me an answer for that. Your answer is correct. So yes, you put this in this way. But then, as you had known the moment of inertia formula, I equal to bh cubed by 12. That h cube effect is this, like that's the effect of this rib reinforcement when you stand on the top. That's how the effect is when you are placing in this orientation. So it's a small, what do you say, game. Initially I had literally no idea how to use a moment of inertia formula. uh, to be frankly speaking, I was really studying hard in the initial days to understand the design, how it works, why is the I-beam theory is very important, and this is how I was able to learn and trial out a couple of experiments to see the actual difference how it plays. And then because this was like an actual, you're playing the life of the people and safety, the design error shouldn't be omitted out the way in which you design. So in this, like, it's not compulsory that you have to have a stiffener like this. There are other ways, like for example, foam, without even the stiffeners, can still play the same role. But then still, if you see the background, the way in which the design works, it will make sure that the stiffness along this direction is very high than this direction. So as I said about the hollow steel rectangular tube was used. So in this case, I didn't use a solid tube. I used with an hollow shaft, but then there were so many thicknesses that had to be considered. Should I go for a 2 mm thickness, 4 mm, 6, or various options that were available in the market? So I had to iterate. Okay, let me try with 60 by 40 or 50 by 50 or 50 by 30. What happens? So there is a lot of iterations with this itself, and then we come to a conclusion whether it is meeting the end goal, that it is not deforming and still able to hold good at all the loads. So the model, what you see here, is an actual model that has been designed, developed, and this is still running in the site. In this was an improved design where you can see is that we made sure that the ribs were also part of the nacelle cover itself, so that it's holding a stronger surface, and also we are eliminating the need for having two gussets and rather than having one gusset. I can show you in the next couple of slides how the complete assembly would look like. So this is how the total assembly is there. What you see in the top, this handrails, they also play an important role. Each of these handrail locations where the bolts are also there, are also called as anchor points. They have to hold 22 kilonewtons of force or load uh, at each location. So that's what the minimum criteria is. This is all, I'm not telling you an arbitrary value. This is all given in the certification point of view, where they're designed, tested, and made sure that everyone is following the norm. This part is the anemometer, and that is also pretty very much crucial. If you lose it, then you are losing almost like where is the wind direction and what is the wind speed that is being fed to the generator. That is also it will also give input to the control systems. What's the actual wind and from which direction the wind is coming from. So the structural stability of this is also important when you're trying to bolt and hook it up on the top of this cover. So as you see, the loads that has to be considered, first and foremost is the wind. That is always that it has got three directions from wherever it can come from the bottom side. Like the wind picks up a lot from the tower external surface and pushes up the cover, but you will not feel anything on the wind on the nacelle cover. As far as nacelle cover is as a whole design is concerned, it will not have any vibration feel or any structural feel due to these effects. What I'm trying to mean here is that in the design of wind turbines, it's not a part that would stop the turbine or that would impair structural defect, or it's like a very high critical thing. It is considered critical, but then the level of criticality is low compared to other components. That is what I'm trying to tell here. So as I mentioned you about in detail modeling, how it looks like, we have to prove that how our model is close enough when you're trying to simulate and show that how your beams and every part of the cover is behaving. We have to also, this is part of the certification to show that how we are considered the model and what each model's function is. So as I was speaking a lot about the certification and following the guidelines, two of the main guidelines is IEC 614-00-1. That's the design of wind turbine. This is available in the internet. There are a lot of free copies that is in circulation. There's nothing wrong. You can download and see how the complete design point of view, the expectation is. GL 2010 is also another guideline which most of the wind farm design people follow. And this is the safety factors that is considered. One is the material safety factor as well as the load safety factor that has to be considered. Now going on to, as these screenshots are from the GL guideline itself. You can see here specifically how to consider the coefficients when you are considering if this is the nacelle cover, if there is the wind flow, what could be the effect of CP. Here it is aerodynamic coefficient from all the directions and 4 directions that we have tried to mention. So every bit has to be complied, and you cannot just omit it. That ignorance, how design engineers do is how to make sure that the safety factor is at least playing its role to make sure that people who are standing or being in close to the inside the turbine, protecting you from any electrical shocks or lightning strikes or any time of the period within the turbine, you are safe inside the nacelle cover. So in India, unfortunately, you don't see much of snow and ice loads. This is predominantly in, for example, in US or Canada, in northern Arctic regions. There have been recent news about in Texas, the turbines did stop because of ice, but that's not in actual practice. There was stopped because of grid failures and so many other reasons. Whenever there is an ice on the length of the blade, in specifically, they have an built-in heating system, like it's a wired heating system to make sure that the blade gets a little bit warmer and the ice would fade off. That's one way. If it is too hard to remove, the only option is like people have to come in and they would climb up or use other techniques to take this ice off. And definitely blade is very much susceptible to damages, like the fracture damages on the skin point of view. It's not problem in terms of structural point of view. As far as snow is concerned on top of the nacelle cover, you cannot really remove it, or there is no specific device to make sure that there is no, if it is also there, it is not going to do any harm. But then the only problem is that it would put additional weights on top of the nacelle covers, and we have to make sure that those weights are also into consideration. So as I was mentioning about different kinds of weights, what you see here is at least 1.5 kilonewtons of force that has to be applied on a 20 centimeter by 20 centimeter area, or you can take it in terms of pressure force to apply the surface area with these loads. So here you can see here small screenshots which I have taken from the guidelines, so that it's easy for you to consider and see like live loads or handrail loads or snow loads or the wind loads, how it has been calculated, and then you can apply. So you will go through a small session on this, on the finite element modeling and technique, how we apply the loads. I will not be able to walk you through the every result of this, but then I have shown in terms of direct results and on actual nacelle cover when from the certification point of view. As I was mentioning, we would take a little bit deviation from the nacelle cover finite element analysis, and we would jump to how I had told you a problem about center of gravity calculation on the window, how it plays an important role. In this picture, what you see is here, like this is the coming from a crane which is holding up the whole drivetrain. This would be probably about 50 to 100 tons. I'm just telling it approximately. Where you could see these belts or the chains are getting inside the nacelle cover and hooking up the whole turbine nacelle cover top. Here also you could see a different picture how they have made sure that okay the load is distributed and they have a made sure that spacer so that the load is equal in all the sides and they're able to lift it. As they lift it to the top of the turbine, the wind starts picking up and this would start swaying. So we have to make sure that the hooking up is very much proper and how crucial this would play. So as far as the center of gravity or the hooking of those places, this is how the lifting hooks is considered. So there would be a rope coming in and there will be a chain that will be hooked up here as well as here. This is how in an actual turbine, this is standing on top of the tower itself, but in a 3D model. But then if you see on an actual site condition, that will be completely different. So what we had the problem was that the window was not in its position, where probably I have to go to a first slide or show. So I have another, yeah. So in this case, what you see here, the window is in this location originally, but then what we found was that when we calculate the center of gravity, we found that it had to be shifted here, and that's where the center of gravity is, and as also it's easy and convenient for the crane people for them to drop the chain and get without damaging the window and assembling it on the top. So how did we do it? So we had to calculate main shaft. Let's say the dimension of the main shaft is there. This would be about 4 meters in length. So the center of gravity would be somewhere in between. So you can calculate if the whole, when this SolidWorks model is given, it is easy that you can define your origin center is here, and then the center of gravity would be somewhere here. That's how this picture would. This picture is like you are looking from the top, and you're looking where on the left hand side is the rotor, and on the rear is the generator side, as you see in the picture. Each of these are the center of gravity of their respective components, and then we calculate using the simple formula in both x and z direction to properly pinpoint where exactly the center of gravity of the whole system would stand. And then it would be making us easier to drop in the chain and easily carry out this operation. It looks very simple when you see at side point of view, but then this is how the background is. So this is the first part of the slide demonstration on the design of nacelle, how the design evolves and develops. I haven't talked about how the pattern and mold is also developed. That is another session altogether. Probably I can have it in sometime in the future later, but then it won't involve any kind of simulation things. It's everything. It's in practice. This would end the first session of the slides. If you have any questions, please let me know. This is one shop floor video photo showing how the mold of this cover looks like. This is in opposite direction. This is the cover, and this would sit inside this and taken out. This is how the final assembly would look like. This is a gearless turbine, just very short, different to the ones which I spoke in the top. Are you all guys convenient and able to follow through what I'm trying to present, or is it good as per your expectation? Please let me know. If you have any questions before I proceed to the demo using ANSYS, how we do it in actual practice. This is how this presentation would go for the next 45 minutes to 1 hour. Probably, if you want, we can have a 5-minute break, and you can let me know uh, when to start again. Right. Right. All these slides will definitely, I can share it with you. You can have it anytime and ask me questions over LinkedIn or on email. Probably the only thing is that you may have to mention what is your subject rather than saying nacelle cover questions or wind turbine questions. I'm happy to help. I've been also a project guide for master students when people were doing their project engineering final year projects for nacelle wind turbine design calculations. Some people were from Crescent Engineering College. Some people were from other foreign universities like in Netherlands who were trying to design some turbine blade design. So if you have any other turbine doubts, feel free to ask. The next demonstration will be completely using ANSYS. This will be also like part slide presentation and part actual in ANSYS itself. For the sake of time, I have already done a couple of simulations, but then we will not be putting all the design simulations. Yeah. Um, yeah. I can show you how the actual model looks like. Are you able to see the screen? Uh, is it okay? Clear? Yeah, so what you can see here, this patch which is highlighted, this is the actual place where the actual window was, and then we moved it here. In terms of its stiffness consideration, this is how where we had to retest it and to see how it was deforming, where the maximum deformation was. As far as nacelle covers are concerned, the major factor is not the stress, unlike it is in an offshore wind farm where the criticality is more. On onshore wind farms, the main thing is what is deformation is the main result that is viewed. So if you look at the bottom side, this is how we place the stiffener ribs, and it didn't play a major role. Where the window was, we still had a stiffener there instead of in this location. We just shifted it, and the deformation started to change its location. So this is the actual. Yeah. So we will start in 8:15. Yeah. Grammar. Yeah. Okay, in this, let me start presenting again. So, if I this one are able to see the slides? Hello. Yeah. Yeah. So this presentation is about how to use ANSYS, specifically the software itself. So I've been using ANSYS for more than 7 to 8 years, right from 2012 and until 2017, until I was in Siemens. Probably I had used 2000, R15 to R17 different versions. So it's not that specific that you have to use ANSYS. You can use also Abacus and other modeling softwares to do the finite element analysis. The technique doesn't only stand with ANSYS. The same technology also exists with other softwares. I would definitely, when I started ANSYS, I had to go for a 3 month rigorous kind of an software awareness on my own, do it by myself. So I would strongly recommend you can go through this reference link website